Welcome to lesson 3 from chapter 10, numerical methods. This is year 2 pure mathematics, and in today's lesson we're going to be looking at the Newton-Raphson method. This is another numerical method with which we can obtain solutions to the equation of the form f of x equals 0. Before we take our deep dive into the Newton-Raphson method, please pause the video and try the 4 warm-up questions. Okay, and let's go through them now. Okay, now question 1 has an interesting setup. We have a curve y equals f of x. The function is not defined any more than that, although we are told that there is a root when x equals alpha, and we can see the root indicated on the diagram here. Okay, so that's the point at alpha 0, the x-intercept. For part A, you're asked to draw a tangent line that cuts the x-axis. So it has to be extended far enough to cut the x-axis at the points with coordinates 4, f4 and 2.5, f of 2.5. So those points are indicated on the diagram for you. So there's 4 and 2.5. So you can just sort of read them off. So you draw the tangent lines here and here, okay, and make sure that they cross the x-axis. If you didn't manage to do that, or if you weren't sure what to do, pause the video again and have another go at it. Okay, so I'll put these solutions on. Okay, so the first tangent line, as we can see, I've just sort of plotted that on there for you. We can see that it cuts the x-axis just slightly. I mean, might not be completely accurate, but we've got an x-intercept just slightly higher than 2.5. And if we put the second tangent line on at 2.5, we've got yet another x-intercept, this time around the 1.5 mark. So we've got these points of intersection that seem to be reducing in value. So the question is, what do you notice about the x-intercepts of your tangent lines? Well, as you can tell, if we actually drew a tangent at alpha, for example, the tangent line would intersect the x-axis at alpha, because the point x equals alpha 0 and the point where the tangent is drawn just coincide. If we move further up the curve from x equals alpha up towards 2.5, for example, the tangent line is going to cut close to alpha but not quite, and you can see that by starting at 4 and reducing the value, so sliding down the curve this way towards 2.5, the x-intercepts just become closer and closer to the alpha that is the root that we're attempting to find. So if you wanted to, you could add some more tangent lines to this. We could take another line, it doesn't matter where we do it, just something arbitrary. So let's say we take a point, let's try and give a point on so somewhere around about here. Okay, and if I put a tangent line on there, I'll try and do it as accurate as I can. So something like that. It's not quite right. Maybe I'll just redo that. So something around about there. You can see that because that point that I've chosen, that arbitrary point, just slightly greater than alpha, the tangent line actually intersects at a point even closer to the root alpha. So there seems to be something powerful in the sense that we draw a tangent line and make sure we extend it through the x-axis, because it seems to, in iterative steps, seems to sort of point us towards the value of the root. So that's the kind of thing we were sort of aiming at with you noticing it in that question. Now, moving on to question 2, we're asked to find the equation of a tangent to the curve with the equation given. So it's one of these transcendental equations. We've got an e to the x term, we've got an x squared term. So it's a combination of transcendental and polynomial. You would not be able to solve this algebraically. So this is something, one of the examples we're going to be looking at probably today. So equation of the tangent. First of all, we need to differentiate our curve. So we'll do that first. So dy by dx. And there's no problem with this. We differentiate term by term. So e to the x is unchanged. X squared becomes 2x and the constant term is lost. So there's the derivative. Now then, at the point 1e minus 2, to get the tangent, of course, we need to sub in the x coordinate to find a value of the tangent, of the gradient, sorry, at this point x equals 1. So we're going to replace the x values with 1. So that's the next step. So when x is equal to 1, dy by dx is going to equal e to the power 1 plus 2, which is just e plus 2. We can leave it in exact form like that. So that's the value of the gradient at the point where x is equal to 1. Now, to get the equation of the tangent, we use the formula for the equation of a straight line. So it's going to be y subtract the y coordinate is equal to the gradient multiplied by x subtract the x coordinate. Okay, and the gradient m, of course, is exactly the same as this value that we've just discovered here. So I'll just say that that is equal to m. Okay, so we sub everything in. So we have y subtract the y coordinate. Now we've got to be a bit careful here. The y coordinate is written in exact form and it's e subtract 2. So just be careful of the signs there. So we're subtracting the whole thing. And that's equal to the gradient, which we now know is e plus 2. So again, I'm going to use brackets. Okay. And then we have x subtract the x coordinate. So that's going to be x subtract 1. All right. So that's the equation. I mean, there's nothing wrong with that answer. We've answered the question, but we can tidy it up perhaps a little bit. So we have y subtract e plus 2 would be equal to ex subtract e, just multiplying it out, plus 2x subtract 2. I'm doing this just to collect like terms, essentially. Okay, now if I make y the subject, I can add e and subtract 2 from both sides. Now, if I add e, you'll notice that the e's will actually cancel out. We've got negative e on both sides of the equation. They cancel. So they're gone. If I subtract 2, I'm going to get negative 4. So let's see what we have. Now we're going to have ex plus 2x subtract 4. Okay, and we can actually factorize this. So we have y is equal to e plus 2, lots of x, subtract 4. So we've got the gradient back. It's in the form y equals mx plus c now, and we now have the y-intercept here, which is your plus c. So c is obviously negative 4. Okay, so just in case you are asked to find the equation in a particular form, that's how to do it. In question 3, we're asked to rewrite an equation, and this is the same process as setting up an iterative formula. So we're essentially asked to write it in the form x is equal to g of x, some function of x on the right-hand side. And the way to do it, or the way I recommend, is to do a bit of rough work first. If you start with the answer and work backwards, and then you can rewrite it forwards. So just do a bit of rough work. This is in case, I mean, you might see what to do straight away. There's no problem with that. But if you don't, then you can do it like this. This will work every single time. So start with the answer. We're trying to get x is equal to 3 subtract e to the x over x. I mean, sometimes it's just not always that obvious. Now, we want to clear this fraction on the bottom because the original equation doesn't have any fractions in it. It's just this form here, the one we looked at in question 2. So if I multiply both sides by the denominator x, what do we get? Well, we're going to get x squared on the left is equal to 3 subtract e to the x on the right. Now that's enough rough work because I can tell now that I need to make x squared the subject. Okay, now if I make x squared the subject, then all I have to do is divide by x and I get the equation that I require. So let's write down the solution now. So I'm just distinguishing between what I consider to be rough work and what is the actual solution that if I was being assessed, I would want to be marked. Okay, so we write out the equation. So we have e to the x plus x squared subtract 3 is equal to 0. I've just discovered from my rough work that I need to make x squared the subject. So let's leave the x squared where it is, and I'm going to add 3 and subtract e to the x from both sides. That will clear the e to the x and the negative 3 on the left. And now to get the formula, I have to divide by x. So if I take all this, divide by x on both sides, and then we get our final step. So therefore we have x is equal to 3 subtract e to the x all over x. And there was obviously a caveat with that. Obviously we'd have to assume that x is not equal to 0. So we wouldn't be allowed to put x equals 0 into that equation because obviously that would create a singularity. All right, so that's question 3. Now moving on to question 4, we've converted this formula into an iterative formula. So we've converted this equation into an iterative formula. So we've added the subscripts n plus 1 on the left and n on the right. And we've got a starting value of x naught is equal to 1. So we have to find the next 3 iterations. So starting with that, let's just plug it all in. So we know that x naught is equal to 1. Notice we can't start with 0 because that would create the singularity. So we need to avoid that. So x1, according to my iterative formula, would be equal to 3 subtract e to the power of x naught over x naught. And just once again, just to be clear, the subscript on the right hand side is 1 less than the subscript on the left hand side. So we can now use our x naught now. So that's going to be 3 subtract e to the power 1. We'll sub it in. Divided by 1. I have to do that in a different colour as well. So divided by the 1. So I can just leave that as 3 subtract e. Leave it exact. Okay, so we've got that. Now for x2, we use our x1. So x2 is going to be, using the iterative formula, 3 subtract e to the x1 over x1. Once again, just looking at the subscript. Subscript on the right hand side is 1 less than the subscript on the left hand side, and we can use our x1 in this. So this is going to be 3 subtract e. Now we've got to raise the e to the power of x1. So that's going to be 3 subtract e in the power, and then we have to divide that by 3 subtract e in the denominator. Okay, so this is going to be an interesting looking number. We could leave it like that, but obviously it's going to make the next iteration really, really bad. So I think the good idea now is to get our calculator, and then we can just set up an iterative formula on the calculator. Okay, so let's do that now. Okay, so I've got the class whiz. Now I'm going to just put in our first x value, x naught, press equals. So that's going to be our first input into our iterative formula. So to set up the iterative formula, just type it in. So it's going to be, I'm going to open a bracket and do 3 subtract e to the x. So that's going to be shift log button, and then I'll put the answer in. Okay, so remember it's the previous answer. Okay, close that, and then we could put all this as a fraction so it looks as it is written, and then we divide that by the answer as well. Okay, so you can get all this from the iterative formula itself when it's given to you. You know from this formula on your calculator, you're going to be using 3 subtract. Now, wherever you see the xn, that's your answer. Okay, and then obviously we have an answer here as well, so that's going to go on the bottom in the denominator. So that's how you would set up your iterative formula. Now, if we do that, of course, that will give us the first value, which is 3 subtract e. Okay, so if you want to, you can write that down as a decimal. So this would be equal to 0.282 roughly to 3 decimal places. Okay, and now if we press the answer key again, we'll get the next answer, which is of course that rather nasty looking thing over here on the right hand side, but that's okay. We know that that is going to be simply equal to 5.944 to 3 decimal places. Okay, now the next one, I'm not going to do any working out for this one. We'll just press the button on the calculator. So x3, just press and equals again, and we get negative 63.682. Let's plug that in. Now you'll notice something about the answers. So we start off with something relatively small. Then we go to something close to 6 and then negative 63. So thinking about the previous lesson when we did iteration, are these solutions converging or diverging? So we're going from 0.282, 5.94, and then negative 63.682. If you're not sure of the answer, just keep pressing the equal sign. I think it's pretty clear what's happening at the moment. So if you just keep pressing it, it's not really converging on anything. It's oscillating. Now it appears to be converging. So that's quite interesting, isn't it? Anyway, so that's the iterative formula. So we found the first 3 terms. I think the first 3 terms are pretty inconclusive in this situation. But if you keep going, we can see that we are tending to converge on negative 1.67. Okay, so let's have a look at the Newton-Raphson method. Right, so this is the introduction to the Newton-Raphson method. And historically, these ideas actually go all the way back to the Babylonian period, and they can be attributed to probably Arabic mathematicians and several other modern Western mathematicians. So this was a technique used by Newton, and it was refined through many processes. And Raphson also has his name attached to it as well. So this isn't the method that Newton actually used initially, which he developed for polynomials, and it has gone through several other mathematicians and has been filtered and refined over the years. And it was actually Raphson who made it an iterative process. So the way to do this is to start with some continuous function. Now it has to be continuous, of course, because we can't have any breaks in the function whatsoever. Any discontinuity would render this completely useless. Okay, so we have to know that this is a smooth curve across an interval, and we also have to have a root at x is equal to alpha. So in other words, we have to be able to solve the equation f of x equals 0 when x is equal to alpha. So alpha being that specific value of x that produces that solution. So the function f must be differentiable. Okay, so that also means that it has to have a derivative that is applicable at every point along the curve. Okay, on the interval that's given. Right. So once we know that a function is continuous and differentiable and it has a root, we can start the Newton-Raphson process. So just before we start, just going back to question 1 in the warm-up, it says here that we discovered in question 1 from the warm-up that a tangent to an arbitrary point on a curve can intersect the x-axis close to a root. Yes, we saw that. And we also saw that by moving that arbitrary point or choosing a point close to the root, the x-intercept of the tangent also moves closer to the root. So we're going to use this principle to develop this method. Okay, so let's get started on this. We're just going to clear that. And I'm just going to scroll down a little bit. So we're going to do this in stages, and we're going to actually derive the Newton-Raphson method right now. So we've got some function f of x. I don't know what it is. It's continuous. It's differentiable probably on the whole real line. Now, I've chosen an arbitrary point x naught. Okay, so x is equal to x naught right there. If you plug x naught into the function, the value it returns, of course, is called f of x naught. This is just a value. It's not a variable because we're putting a particular value of x into it called x naught. Now then, our first task is to draw a tangent to the curve at that point. So I've already done this. I'm just going to hopefully bring that up. So there it is. Okay, so that's my attempt at a tangent. You can see that in red. So what does this do? Well, this gives us our next input, essentially. Now, because we've got a tangent to the curve at that point, we can then use this to develop another tangent, and then another, and then another, and it becomes an iterative process. So let's just develop that idea and see how we can actually do that. Well, let's just have a look at the equation of this tangent first of all. So this is going on to step 2. We've drawn the tangent at the given point, and to write down the equation of the tangent, or to calculate the equation, we just need to do a few things. So I'm just going to do this in the space above the graph. So we know that y is equal to f of x. Now, if I want to find the derivative of f of x, which I'm going to need to find the equation of the tangent, I just simply call that dy by dx. Okay, and the derivative of this, we just use the notation f dash x, as you're familiar with. So we can call that the derivative at any point along that curve. Now, at a particular point, x naught, so when x is equal to a specific value x naught, we now know that the derivative dy by dx is going to take on a specific value as well. And we can call this f dash of x naught. I'm just going to put that x naught in a different color just to highlight it. Okay, now that value of the gradient is a value. It's not a variable. Okay, so this is your m, essentially. Okay, at x is equal to x naught. So we've just worked out, and it's symbolically and generically, what the value of m would be at an arbitrary point x naught. Okay, so we need the equation of the tangent. Well, we've got the coordinates. We've got them right here at that point. So we can now sub those into the equation formula for a straight line. So we know the equation formula for a straight line is as follows. So it's going to be y subtract the y coordinate is equal to the gradient multiplied by x subtract the x coordinate. Okay, so we sub everything in now. So this is going to give us y subtract the y coordinate, which is f of x naught, the green one that I've highlighted. Okay, green by, I mean right here. Okay, that's the y coordinate, is equal to the gradient, which we now know is f dash of x naught. These are all constants. They're all particular values. And then we multiply that by x, subtract the x coordinate. So that's going to be x subtract the x coordinate. So that's going to be x naught. So you see how generalized this is. So that's the equation of the tangent. So this is the tangent at the point x naught f of x naught. Okay, so that's a really important result we've just derived here. Okay, so I'm just going to highlight that. So that's step 2. So we've got the equation of the tangent. Okay, and we can write this in the space provided. I've just done all the working out. So if you want to write it over on the left hand side, you can do that. Just be careful when you're writing the gradient. It's f dash x naught. That makes a huge difference, of course. And then x subtract x naught right there. Okay, I apologize if you didn't have enough space. Now then, for step 3, okay, we've got the equation of the tangent. Now, this is the Newton-Raphson method in action. So we know that the tangent intersects the x-axis. Okay, that was one of the things we stipulated in the first question in this lesson. We said, make sure that your tangent is long enough to intersect the x-axis. And our tangent intersects the x-axis somewhere between x naught and alpha, or I should say alpha and x naught if it's in order. Now, this is a given. So given that the tangent intersects the x-axis, we have to find an expression for x1 in terms of x naught. So we're going to give this point on the x-axis a name. So this point of intersection is called x1, 0. So what we do is that point is going to provide the next iteration. So that x1 is going to be our new input, and we're going to figure out what the tangent would be at the point on the curve when x is equal to x1. Now, you'll see what I mean in a second, because I'm going to draw this on the diagram. So on the diagram, we can find the point on the curve where x1 is substituted into the function. So if I just draw a vertical line upwards like that, okay, so I've now got a point on the curve. Now, this point here, I'm just going to highlight it. This has a particular value as well. So this point right here has coordinates x1, okay, and f of x1. Okay, so the x coordinate is x1 this time, and the y coordinate is f of x1. So we can now draw a tangent to the curve at the point x1, f of x1. So let's do that. Let's try and draw a tangent to the curve here. Right, so I'm going to try my best to do this. It's going to come down. Oh, that's not very good. Let's try again. It's going to be more like this, I think. That's not too bad. Hope yours is a bit better. Make sure your tangent crosses the x-axis. Okay, so my pink line is the tangent at the x-coordinate x1 and with y-coordinate f of x1. Okay, so you can see now this would generate another point on the x-axis. We've got this point here. Now we could call this point x2 and 0, okay? Notice that we're getting closer and closer to our root alpha. And if you make x2 your input, which you could do, we could just draw a vertical line from x2 up to the curve, draw another tangent, and then repeat the process ad infinitum. You're going to get closer and closer to that value of alpha. Okay, so let's see what this actually does and see if we can create and derive an iterative process. So we've got a point on the curve. Now, this point x10 that I've got written over here in step 3, we know this point lies on the tangent because it's the point of intersection of the tangent, our first tangent, with the x-axis. So I can actually sub that pair of coordinates into my equation for my first tangent here, which is the red line. So if I do that, let's see what happens. So this, so x1 is the x coordinate, so and 0 is the y coordinate. So I'm going to have 0 first of all, subtract f of x naught. So notice that the variables in this tangent equation are the y and the x here. Okay, everything else takes on a particular value, and not variables. So this is going to equal f dash of x naught, and then we're going to multiply that by x1 subtract x0. Okay, and it asks us to find an expression for x1 in terms of x naught. Oh, well, that's okay. The 0 is just irrelevant, so it's going to be negative f of x naught is equal to f dash of x naught multiplied by x1 subtract x naught. Now, what I can do is to get the x1 part here on its own, what I really need to do is divide both sides by this, or I could multiply it out first, but I think I'm going to divide both sides by that derivative. So let's do that next. So we're going to have negative f of x naught divided by f dash of x naught is going to equal x1 subtract x naught. Okay, and then if we add x naught to both sides, we've got an expression for x1. So that's going to give us x naught subtract f of x naught divided by f dash of x naught, and that's equal to x1. Now, notice what we've got here. We've got x1 expressed purely in terms of the previous point, okay, purely in terms of x naught. So we've essentially got an iterative process going on. And I know it's the other way around, but everything on the right-hand side, the subscript is one less than the subscript on the right-hand side. So we can use this as an iterative process, and that will be the next step. And we're almost ready to write down the Newton-Raphson method. Okay, now step 4, I kind of glossed over that in my explanation. So yes, you would repeat the process as I showed you on the diagram by taking the x-intercept of the tangent, the second tangent, and then inputting the x-intercept as your x-input for the next point on the curve, drawing a tangent there, and the x-intercept will form the point on the curve for the next tangent, and so on and so on and so on. So you converge on that route alpha. Now, what we saw in our first iteration that we did is we actually managed to write down what is called the Newton-Raphson method. So we've got the subscripts here, 0, and they are one less than the subscript here on the left-hand side. So more generically, here we have the Newton-Raphson method written out in full. Okay, so notice that this method hinges on the derivative. Okay, we need to know the derivative of the function. So obviously it's got to be differentiable and it has to be continuous for this to work. So those are just some of the parts of the definition that we need to be aware of. So just going through the explanation, it says that the Newton-Raphson method is an iterative procedure. Yes, using tangent lines. Now, the value of xn plus 1 is the x-coordinate of the point where the tangent to the graph at xn fxn intersects the x-axis. Yes, so that's using the x-intercept to generate the tangent, or the point on the curve that will generate the next tangent. Okay, it's probably easier just to do it, to draw it out yourself, just to convince yourself of what's actually going on, which we've already done. Now, there's a couple of things we need to be aware of before we go and try out this technique. Now, these are the practical limitations. So I'm just going to clear those annotations, just scroll down a little bit because we need to be aware of this. The practical limitations are to avoid turning points. Now, you'll see from the way the Newton-Raphson method is written that we have an issue with having this fraction term here. Now, the denominator, as you know, for any fraction is not allowed to equal 0. Okay? And it's a derivative. So if you have a situation where you have f dash of one of your iterative x values is equal to 0, this is a stationary point. Okay? And if it's a stationary point, then it's likely that it's going to be a turning point. Okay, and turning points are bad. And you'll see from figure 2 the key problem of choosing your or getting an x input as a turning point. So if we have this is just for the first iteration. If you choose your x naught to be at that point there, and it happens to be a turning point, your tangent line is never ever going to intersect the x-axis, simply because it's a horizontal line. So it's just simply not going to work, and you will get obviously a singularity right here because you're dividing essentially by 0. So you avoid turning points at all costs. Okay, if you didn't know it was a turning point, just try another point as your starting value, but you will be given the starting value, I think, in most cases. Now, the second point that we need to be aware of is quite similar. Now, if you choose a starting value, let's say x naught, and it's too close, so not a turning point itself, but very close to a turning point, there's going to be another problem because the derivative is going to be not 0, but close to 0. Yeah, and it's either going to be positive or negative. Now, what that means is if you have a turning point that is close to 0, your tangent is just going to be way out. It's going to create your next iterative point, which is at x1. And as you can see from this diagram, it's just too far away from the curve. And the Newton-Raphson method then dictates that you have to use your x1 over here as your next input. And if you did that, you would have to draw a line up to the curve right here, and I can't even fit it on the diagram. The curve would continue somewhere up here, for example, and then you're just going to be way off. Okay, so we need to avoid that at all costs. So avoid turning points is the message. Okay, I think now we're ready to have a go at an example. So we're going to do one worked example, finding roots using the Newton-Raphson method. The process is the same for each question. So there are a few different things that can be asked. So this is taken from an exam format. I've combined several different types of exam question to cover all the things that you might be asked on the Newton-Raphson method. So this question, we've got a polynomial degree 3, it's a cubic. I've specified a point where x is equal to lambda, and this is the stationary point on the curve. So you can see it on the diagram as well. The point P alluded to over on the left-hand side right here, which has a function value of f of lambda, is a stationary point. Okay. We're also told that the equation f of x equals 0, okay, has a root alpha, and alpha is between 2.8 and 2.9. All right. So first thing to do is to explain why choosing x naught equals lambda would not be suitable when applying the Newton-Raphson method to find an approximation for alpha. Well, we saw this just on the previous page. We know that if we're using tangents, which is what the Newton-Raphson method does, to to find x-intercepts of the tangents to generate new points on the curve whereby more tangents are drawn. Those tangents have to intersect the x-axis in order to do that. Now, in this instance, if we draw a tangent at the point P, which I've just missed it, but never mind. Let me just move it a little bit. So if we, there we go. So if we draw a tangent there, you can see that the tangent will never intersect the x-axis. So that would be the reason. So I'll just write the answer on here. So explain why choosing x naught equals lambda would not be suitable. So we could say that the tangent would be, so assuming if you did do it, would be a horizontal line or straight line consequently. I'm just going to write this underneath. You use the space obviously that's provided on the page. This would not intersect the x-axis. And how does this manifest on or in the Newton-Raphson method? Well, the problem at P, of course, is that because it's a stationary point, if we work out the derivative of the function, so the derivative at x equals lambda is of course 0. Okay, and the Newton-Raphson method states that the derivative cannot equal 0. All right, so I'll just jot down the Newton-Raphson method. It's in the formula booklet, so you don't need to worry about remembering it. But this is the form it takes. So the reason why it'll be a problem is if you have a derivative which is 0, that creates the singularity, okay, which is right here. So that denominator can never equal 0, okay, for obvious reasons. Okay, so there's a couple of ways of exploring that. Saying that the tangent is horizontal, which wouldn't intersect the x-axis, and the fact that you have the derivative at that particular point in the denominator could never be 0 because you cannot divide by 0. All right, so for part B, show that the Newton-Raphson formula for f of x can be written as given. So I'll just pause and then we'll do this, and we'll use the full page to go through each of the steps here, and then we can use the Newton-Raphson method in part C to perform an iteration, and I'll show you how to do that on a calculator. All right, so I've just written out the formula, the equation, I should say, for f of x, and I've also written down the Newton-Raphson method as it's presented in the formula booklet. And we have to show that the Newton-Raphson method can be represented as that single fraction. So what we'll do is we'll kind of substitute our f into the Newton-Raphson formula. So you'll notice that we have f of xn in the numerator and f dash of xn in the denominator, first of all. So we'll start with that. So what we'll need to do is to just write down what f of xn would be. So we just put the subscript in. So f of xn, it's just replacing x with a subscript n for the iterative formula. So that's your input. So it would be xn cubed subtract 3xn squared okay, subtract xn and then add 4. Okay, so that would go in the numerator that I just highlighted a moment ago. So the numerator over here. Okay, and then we have to find the derivative of f of x. Well, we'll do the derivative first, and then and this is just a polynomial derivative. You won't have to do any kind of complicated differentiation for this. That's not the idea. It's about using the process. So f dash of xn, we can start with that. So if we just bring the power down, take 1 off the power, so that's going to be 3xn squared, subtract 6xn. Okay, don't worry that it's a xn with a subscript, just differentiate as normal, that's fine. Okay, and subtract 1. Okay, if you prefer, just go back to the original f of x and just differentiate this. So like 3x squared, subtract 6x, subtract 1, and then just replace the x's with xn's, and then you've got the same thing. Okay, so we're ready to set up our Newton-Raphson method now. So to do that, we just copy down the formula. So we know that the Newton-Raphson, solving an equation f of x equals 0, it has to look like this. So to generate the next term, we use the previous term's tangent, so it's going to be subtract. Now I'm going to replace the numerator with what we have for our f of x, so I'm going to use brackets here. So that's going to be xn cubed, subtract 3xn squared, subtract xn plus 4. Okay, so that's just f of xn in the numerator, and then in the denominator, so just put that in, we put our derivative. So that's going to be 3xn squared, subtract 6xn, and then subtract 1. So that's essentially it. We've got a Newton-Raphson formula, but we have to show we can write it in a particular way as a single fraction. So at the moment, we don't have a single fraction. We've got a 2-term expression on the right-hand side. So to combine fractions, we need to multiply. We need to find a common denominator. This is obviously going to be the common denominator. So I need to multiply the xn by the denominator and then collect like terms. So let's have a look. So let's do that. So it's going to be xn multiplied by, we'll put it all in, 3xn squared, subtract 6xn, subtract 1. Okay, and that's going to be over 3xn squared, subtract 6xn, subtract 1. So you can see how they would just cancel, but we do have a common denominator now. So subtract xn cubed, subtract 3xn squared, subtract xn plus 4. Okay, and all that is over the same denominator. So 3xn squared, subtract 6xn, subtract 1. Right, so what we're going to do now is we're going to expand the numerator on the left-hand expression right here, and we're going to write it as a single fraction. So let's do that. So this is going to be 3xn cubed, subtract 6xn squared. So the xn's will increase by a power of 1. Subtract xn. And please use the brackets, maintain the brackets, because we're subtracting, so we don't want to make an error with the signs. So subtract xn cubed, subtract 3xn squared, subtract xn plus 4, and that's all going to be over, so it's one big fraction. 3xn squared, subtract 6xn, subtract 1. Okay, so it might seem a bit laborious, this, but we need to make sure we get this right. Now, what I can do is I can now expand the bracket on the right-hand side just by changing the signs and then collect like terms to get our final expression. So this is going to be 3xn cubed, subtract 6xn squared, subtract xn. Now then, because I have a negative in front, here, multiply everything by -1. So I'm just going to do that. So this is going to be subtract xn cubed plus, because we have I know I'm laboring this, but it's important to get this right. We have a negative there and a negative there, so they become positive. 3xn squared. Then we have another double negative, so that's going to be plus xn, and then subtract 4. Okay. Oh, obviously, please skip ahead. If you're comfortable with this, there's no issue. Just skip ahead. It's fine. All right, and then we've got the denominator. So let's collect all the like terms. So let's have a look at our xn cubed first of all. Well, we've got 3xn cubed there. Subtract 1xn cubed, so that's going to give me 2xn cubed first of all. Okay, and let's have a look now at the xn squareds. So we've got negative 6xn squared there, plus 3xn squared there. So that's going to be negative 3xn squared. And the good thing is, because this is a show, that if there's anything that's amiss while you're doing this, go back and check your working. You know, it's not always obvious that you've made a mistake. Okay, let's have a look now at the negative xn. So we've got negative xn there. Sorry, the xn's I should say. The negative xn and a plus xn, so they're going to cancel. So we're just left with subtract 4. Okay. And then all over 3xn squared, subtract 6xn, subtract 1. And there we have our Newton-Raphson method rewritten, okay, as required. So now for part C, we're ready to use our Newton-Raphson iteration formula. We're told to start with x naught is equal to 2.8, and we're going to give an answer an answer to 3 decimal places. Okay, now we can type this into our calculator and let the calculator do the work essentially. So if first up we just put in 2.8 and then just press equals, you can change that to a decimal as well. Now we're ready to go. So to plug in the formula, now we've just got to be a bit careful and make sure that we reproduce the formula exactly. And you're substituting in the previous result. So we're going to be substituting in x naught into all these positions to generate x1. Okay, as we've done iteration a few times now. Okay, so I'll just write that out just so we're clear. So x1 is going to be equal to 2 lots of x naught, okay, cubed, subtract 3 lots of x naught squared, subtract 4, all over 3 lots of x naught squared, subtract 6 lots of x naught, okay, and then subtract 1. Now, obviously, you can translate the x naught into just an answer on the calculator. Okay, so wherever you see an x naught, that just becomes the answer. Right, on the calculator then. So let's plug in the formula. So I'm going to open a bracket, and it's a good idea, of course, because to open a bracket just so we're dividing by we're dividing the whole of the numerator by the whole of the denominator. Okay, and I'm just going to, on the calculator, let the x naught is going to equal the answer key. Okay, so let's do that. So opening a bracket. Oh, that's the wrong. Let's do that again. 2.8. Let's plug that in. Okay, so opening a bracket. So we have 2 multiplied by the answer cubed. Okay, just come out of that. Subtract 3 multiplied by the answer squared. Okay, subtract 4. Now that's the whole numerator, so I'm going to close the bracket and I can put that as a fraction, pressing the fraction button, And then we have, I'm going to open a bracket again, 3 multiplied by, you don't have to, but I just do it anyway, it's habit, because I'm used to old-fashioned calculators. Subtract 6 lots of the answer, okay, and then subtract 1. Okay, so there's our Newton-Raphson method on the calculator, and you can see wherever we had an x0 over here, okay, I've replaced it on the calculator with this answer function, okay, in every position. So at this point, just double check that they match up, okay, before you do anything, because otherwise you'll have wasted your time. So everything looks fine now, so we can just go ahead and press the answer key. Now, what this is going to give us, this is going to give us a value for x1. Okay, so we'll be ready to jot this down. So therefore, x1 is just going to equal, and we'll see what it is. Okay, so we've got 2048 over 715. I'm just going to change that into a decimal. So that's 2.8643. Dot, dot, dot. Okay, which is, and we'll give this to 3 decimal places. We have to do two more iterations, but so that's 2.864 to 3 decimal places. Okay, and then all we have to do for the next iteration is just press the answer key again. Okay, so very subtle change. It must have been pretty close. So we now get 2.8608. All right, dot, 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 which is equal to 2.861 to 3 decimal places. Okay, so we've done the 2 more iterations. We've used the calculators, nothing wrong with that. That's our answer for part C right here. So now we have to show in part D that this answer is indeed correct to 3 decimal places, and we have to use a suitable interval. Now, when it says that, this is another bounds question. We're going to use upper and lower bounds, which is what you did at GCSE. Okay, so just write down part D. So if we check this, so this is the root essentially. So we're going to check that alpha, our root, is equal to 2.861 to 3dp. That's what we have to confirm. All right, so let's create an upper bound. Now, to do that, of course, we can write alpha is equal to 2.861. I'm just going to add 1 extra decimal place as I do. And then if we focus on those last 2 digits, okay, this seems to be, looks like 10, doesn't it? Okay, so I can create an upper bound and a lower bound for alpha. So alpha upper bound, we'll call it alpha with a subscript UB, is going to equal 2.86, and then I add 5 to that 10. I know it's not 10, and it's naughty to say 10 when we're talking about decimal places, but if you add 5 to that, that's obviously going to be 15. So 8615. Okay, and then for the lower bound, we subtract 5 from that 10. So alpha lower bound is going to equal 2.86. That's not going to change. Subtract 5 from 10, so that's going to be 0.5. And going back to the first lesson on numerical methods from this chapter, to show that this is correct, there should be a sign change. Okay, remember that f of alpha, if it's a root, is equal to 0. That's what we're told. So we know that alpha is the solution to the equation f of x is equal to 0. Okay, so when x equals alpha, we know that that's true. Okay, that's the whole point of this. So when we plug in the upper bounds and the lower bounds, we're not expecting to get 0, but we are expecting to get a subtle change between positive and negative, or vice versa. So what we have to do is just inspect what happens when we plug in f of the alpha upper bound, okay, and f of the alpha lower bound, which we'll do in a second. So the upper bound, as we've just discovered, is going to be f of 2.8615. All right, now we can plug all that into the calculator. So let's do this. So just be careful when you're plugging the numbers in. We're plugging this into the original function. Okay, so the original function is x cubed, so 2.8615, that's cubed. Then it's subtract 3 lots of 2.8615 squared. And then we have to subtract x. So this is the original f of x, okay? Subtract x, that's 2.8615, and then add 4. Okay, so I'll just jot that down just to remind you, because it's not on the screen right now. So we know that f of x also is equal to x cubed. This is the original function. Subtract 3x squared, subtract x, and then plus 4. Okay, so let's see what we get from that. So we plug in those numbers, and we get a very, very small positive number, as we'd expect. So this is equal to, I'm just going to write this as not in standard form, so 0.004, I think that's right, 4367, so 43, I'll put 436 ... Now that's positive, okay? So we'll just make a point about that. That's a positive number. It's very small, but it's positive. Okay, now if we check the lower bound now for alpha, so f of alpha lower bound is going to be f of, now we plug in the lower bound, which was 2.8605, which we just determined previously. Now we can plug this in, and I'm just going to edit what's on the calculator already. So if we go back to the calculator input, and you can do this, the only thing I need to change is the 1 to a 0 in each of these. Okay, so it's 8605 across the board here. So just delete that, put a 0 in, and just delete that and put a 0 in. And it is a good idea just to check everything's okay. So 2.8605 cubed, subtract 3 lots of 2.8605 squared, subtract 2.8605 plus 4. So we're expecting, if this is true, we're going to get a negative result here. Okay, and yes, we do. So we have negative. So again, it's in standard form. So it's 0.001953 plus some other stuff, which is just negative. All right, so that confirms that we have a root, because both of these numbers, these bounds, although on the face of it they don't both round to the same number, because we've taken a result accurate to 3 decimal places and formed an upper and lower bound, we know that it must be accurate to 3 decimal places. So let's just write that down now. So that we have the change of sign. So the change of sign indicates that, and we can just restate what alpha actually is. That alpha is equal to 2.861 to 3 decimal places, because we've checked the upper and lower bound and we get the sign change. So that's pretty conclusive. Now, that's using the Newton-Raphson method, and of course we could have done several iterations and got something way more accurate just by pressing the equals button over and over again. Now, if you want to actually figure out what the actual solution is, if we have a polynomial situation, what you can do is you can use the equation solver on your calculator. So I'll just show you this in case you're not sure. If we just cancel all this, go to menu, go down to your equation solver that you use for your quadratics, select that. Now, this is a cubic, so we're going to select a degree 3 polynomial, and we can try and solve this. Now, the function itself was 1x cubed, subtract 3x squared, so we'll put that in, subtract x, so subtract 1x and then plus 4. Okay, now, so if we press equals, let's see what the roots are. So we have a root at negative 1.11, and the second root, x2, is at 2.8608. Now, this is the equation solver telling us the answer. Now you can see it's pretty close, and in fact that it is accurate to 3 decimal places, and we could have got an answer just as good using the Newton-Raphson method, and it wouldn't have taken many iterations to do that. And to finish off our work on the Newton-Raphson method, we're going to have a look at a modelling application, and this one comes from astronomy. Now, in astronomy, planets move along elliptical orbits, and I've put some links into this paragraph here if you want to find out more about it. But there's different ways of measuring the position of a planet. You can use something called the eccentric anomaly. There's also something called the mean anomaly, which takes the average position when you basically assume that it's traveling on a circle. And also there's something called the true anomaly, which is not featured in this, but is the position relative to a focal point of an ellipse to the actual position of the planet. And all these different measures of the angles are all linked together. Now, one of the interesting piece of information that comes out of this is Kepler's equation. Now, Kepler's equation allows us to link the mean anomaly, which we call M, to the eccentric anomaly, which we call E. And it's what we call a transcendental equation. So you cannot solve this equation algebraically. Okay, so we have to use numerical methods in order to obtain a solution. So in astronomy, it's quite easy to determine the mean anomaly of a planet because you can just take the whole orbital period, divide that period, or divide 2 pi by that period to get the position, the average position. But then to get the eccentric anomaly, which is a bit more realistic, you have to solve this equation. So the mean anomaly is quite easy to obtain, but getting the eccentric anomaly requires a solution to this equation. So again, if you're interested in this stuff, please just follow the links and you can have a look at it. And there's also videos on YouTube that show derivations of this. Right, so just for a bit more information, the 0.1 in this equation represents something called the eccentricity of the elliptical orbit. Now, the planets have slightly eccentric orbits. They're pretty much non-circular. The Earth's orbit is quite circular, but the orbit of Mars, for example, is slightly more eccentric. And the eccentricity refers to how circular the orbit is. So if you take a circle itself, something like that, then the eccentricity would just be 0. It's not eccentric at all. But then if we took an ellipse, something like this, this eccentricity would be somewhere between 0 and 1. And then to make something completely eccentric, this would be a straight line, which would have an eccentricity of 1 exactly. So that's what eccentricity is. It's just how elliptical the orbit actually is, or the shape. Okay. So moving on to our Newton-Raphson question, the astronomer in this situation is interested in predicting the position of a planet at a given time, which is something they might want to do. And they're interested in the mean anomaly at pi over 6. So this is in radians, okay? This is an angle measured in radians. And what we have to do is set up a Newton-Raphson equation to solve the equation when m is equal to pi over 6 and obtain an accurate value for E. So for part A, we have to show that this value of E is the root of this function, and we have to determine what this constant K is going to be. Okay, so I'll just pause there, and we're going to use the full page, and then we're going to actually use the Newton-Raphson method. So I've just written out Kepler's equation here, and we have two variables in play. Okay, we have the independent variable, which is what we want to solve for, is called E, capital E, the eccentric anomaly. Okay, the eccentricity is 0.1. That's fixed because that's dependent on which planet you're talking about. And then we also have the dependent variable, okay, which is m. Okay, and that's the bit that's easy to deduce. Okay, once you know a planet, what the planetary orbital period actually is. So just to think about this in terms of variables, you could plot a graph of this situation. You could have, for example, the x-axis here and the y-axis going like that. Now, the x-axis is called the e-axis in this situation. This is where we would plot the eccentric anomaly, because this is the independent variable, and m would be the vertical axis, this the dependent variable, and you have the origin there. And E is only defined for positive values, so you'd only have the positive branch of the E axis or the X axis. So to get this into more familiar language, what we can do is we can just change the names of the variables essentially. So we can go back to talking about X and Y. So E would be the X axis and M would be the Y axis. So I can rewrite my Kepler's equation using these variables instead. So it looks a little bit more familiar. So we're going to have y is equal to x subtract 0.1 sine x. Okay. Now, so that would be a more mathematical way, just removing ourselves from the physics side of things. And now we can say, okay, well, we've got a fixed value for our mean anomaly. It was pi over 6. So if we know, so I'll just write down what we know. We know that m is equal to pi over 6. We want to find out what x is when this happens. So that implies that y is equal to pi over 6. Okay, so we can now sub y is equal to pi over 6 into this equation. So this is what we're going to get. So we're going to get pi over 6 is equal to x subtract 0.1 sine x. Okay, and if we want to use the Newton-Raphson method, just to recap, in the formula booklet, it's written as follows. So it's when you have an equation, f of x is equal to 0, then you can set up your Newton-Raphson iterative formula as follows. So xn subtract f of xn over f dash of xn. So we need to set up an equation equal to 0 in order to use the Newton-Raphson method. So I can subtract the pi over 6 from both sides here. So therefore, we've got 0 is going to equal x subtract 0.1 sine x subtract pi over 6. All right, so that's what that constant k is all about. So we've now got an equation equal to 0. So therefore, we can now say let f of x equal the whole of the right-hand side. So x subtract 0.1 sine x subtract pi over 6. And this is the equation we're going to use for our Newton-Raphson method. So I hope that makes sense. We know that when f of x is equal to 0, that will give us the solution that we need, which fits with the mean anomaly being pi over 6. Okay, so let's go and use our Newton-Raphson method now. Now, we only have to perform one iteration for the Newton-Raphson method. And if we set it up on our calculator, you can make your answer as accurate as you like. But in this instance, we're given a starting point. So we know that x naught is equal to 0.6. Okay, so given a starting point, and now we've just got to write out the Newton-Raphson formula. So to do that, I'm just going to start off with going back to our f of x. We're going to need to differentiate this. So differentiating f of x. So we need to find f dash x, and then we can write down our iterative formula. So f dash x is going to equal, so just differentiating f of x term by term. So firstly, we've got the x term here. That's just going to become 1. And such a great property of differentiation being a linear operator. Just doing it term by term makes it so easy. The second term, so it's negative 0.1 sine x. So we've got to differentiate this. So the sine x it's a standard result, becomes cos x. And there's no sign change, so that's just going to be subtract 0.1 cos x. And then the constant term on the end, the negative pi over 6, is just going to disappear. So that's the derivative. Now we can write down our iterative formula. And we don't have to write it in a particular way, so we'll just keep it really simple. So we have x the n plus 1 is going to equal xn subtract. Now I'm going to use brackets here to make sure I don't make any errors with the sign. So I put my fx in the numerator. So it's going to be xn, remember with the subscript, subtract 0.1 sine of xn, subtract pi over 6. Okay, that's the numerator. Okay, and just divide all that by our derivative that we just found. So that's going to be 1 subtract 0.1 cos of xn. So you'll see all I've done is just, instead of having an x variable, we've got xn's all over here. Just make sure that you've got that as well in your notes. And we now have our iterative formula, so we can perform one iteration. And like I said, you can, if you program this into your calculator, you can do numerous iterations. So I've now got my calculator ready. I'm just going to plug in the first value, which is 0.6. There we go. We'll plug that in. That's 3 over 5, obviously. Just change that back to a decimal. And now we can say what x1 is. So for x1, obviously, it's going to be x0 subtract, now it's going to be x0 in the numerator, subtract 0.1 sine of x0, subtract pi over 6, all over 1 subtract 0.1 cos of x0. So once again, we replace all of these with 0.6, and we do that on our calculator. Okay. So let's do this. So 0.6 is the answer. So I'm going to have answer, subtract, let's open a bracket, answer again, subtract 0.1. And I forgot to mention, but make sure you're on radians, of course, here. It's really important because we're using trig here. All right, let's continue. So 0.1 multiplied by the sine of the answer. Okay, and then subtract pi over 6. Okay, just come out of that and then close that bracket. So that's the whole numerator done. Now, I'm just going to set that as a fraction. Now, if I do that, just make sure that you have the answer subtract on the left-hand side, like I have here. Okay, and it hasn't been included in the fraction, so that looks okay to me. So let's continue with this. So we're going to put in the denominator 1 subtract 0.1 multiplied by the cosine of the answer. All right, and there we have it. So that's the iterative formula. Now this will generate x1. So if we press equals, we get an answer. So that's 0.5782. And rather disappointingly, we only have to do this one more time, but it would be nice to do a few more. So x2 would equal 0.57829695, etc., etc., etc. And we need this to 3 decimal places. 0.5782, 3 decimal places. So the question is this a good approximation? Well, we test it by using our numerical methods from the first lesson, where we determine roots. So we're going to look for an upper bound and a lower bound and determine whether there is a change of sign or not. So the x2, sorry, it's x1, isn't it? I've written x2 for some reason. So the x1 looks pretty good. So let's test whether it's actually correct to 3 decimal places or not. Let's just remove the calculator. Okay, so I've just moved the calculator slightly. I'm just a bit stuck for room here. So let's have a look at the bounds. Now, for x1, we've got 0.578. So we're assuming this is pretty close to the root alpha. So we're going to say let alpha equal 0.578 3 decimal places. I mean, what we're actually doing is, I'll put a question mark around that because we're actually going to check whether that's the case or not. So let's do the upper bound and the lower bound. So I'm just going to move up to the left-hand side here. So the alpha upper bound. Now remember, of course, if we just write the number out again, alpha is 0.578. If I just add an extra digit onto there, okay, and then I can focus on those last 2 digits and then just add 5 and subtract 5. So it shouldn't be a problem. So if I add 5 to that, that's going to be 0.5785. So that's my upper bound. And my alpha lower bound is equal to 0.57. And then if I subtract 5 from 80, I get 75. So those 2 bits on the end, the last 2 decimal places, the 3rd and 4th, those are the bits that have changed. And we now sub those into our f of x equation. Now, it's not the iterative equation. This is the equation that we derived in part A. So we know that f of x, I'm just going to write it down here, was equal to x subtract 0.1 sine x subtract pi over 6. And that's the one we're going to be using. Okay. Which is Kepler's equation with slight modification for the Newton-Raphson approach. Great. So let's plug our upper bounds and lower bounds into the calculator and see if we get the change of sign that we want. So we're going to do f of alpha upper bound first of all, which is of course f of 0.5785. All right, so I'm just going to plug all this in and let's see what happens. So go back to menu, option 1. And remember, of course, you need to be set on radians for this as well, because we're dealing with trig. Okay, so let's plug everything in. So we're going to have 0.5785 as my x value, subtract 0.1 multiplied by the sine of 0.5785. Okay, and then I have to subtract pi over 6 from that. Okay, so hoping for something pretty close to 0, but we don't know if it's going to be positive or negative just yet. Okay, oh, that's very small. Okay, and it's very positive. Well, it's not very positive, but it's positive nonetheless. So this is going to be 0.000224. Okay, which is, and some other stuff, which more importantly is positive. Okay, so you see how close that is to 0. That suggests we've got a pretty accurate representation of the root here. Now let's sub in the lower bound. So f of alpha lower bound. Now again, you've got more space than I have. I'm trying to squeeze things in to get everything on the screen. So use the space that you've got. And I'm just going to go back and just edit what I've inputted and just changed the number to 0.5775. Okay. There we go. Right, so if we plug that in, let's go back in editing. So pi over 6 is fine. Just go back to that. So we're going to have to delete the 8 and replace that with a 7. And just delete the 8 again and replace that with a 7. So just check that that's correct. So it should be x, subtract 0.1 sine x. Yes, looks good to me. Press equals. Okay, and we have a very small but negative number, as we would expect. So we have negative 0.0006918, etc., etc. I've not rounded that, which is negative. Okay, so we've now confirmed that this is accurate to 3 decimal places. So we just make a statement now. So we say the change of sign indicates that alpha is indeed 0.578 to 3 decimal places. And of course, the astronomer or whoever's doing this can, depending on however accurate they want the root of this equation, how accurate the position, they just do more and more iterations, and you can get a calculator or a computer to do that for you. Okay, so that concludes that example, and that's numerical methods completely finished. Please try the questions, and if you're interested in the astronomy stuff, please follow the links in the notes.